Hi folks, Mrs. Gates here. Today we are going to talk about how we can use graphs of motion to help us calculate things like displacement, velocity, and acceleration. Let's go ahead and get started with a little bit of review about some of the terms that we've already talked about. Let's start by reviewing what we mean about velocity. Recall, velocity is defined as the rate at which something's position is changing. Thus, if we're looking at a graph of something's position as time changes, we are simply looking at the slope of the graph, the rate of change. If something is not moving with a constant velocity, we might have a position graph that's a curved line. In that case, we look at the slope of the tangent line at a particular point. This gives us the instantaneous velocity of the object at that moment, the rate at which its position is changing at one instant. Similarly, acceleration is defined as the rate at which velocity is changing. That means if we're looking at the graph of an object's velocity as time passes, the acceleration is simply the slope of this line. Let's consider what this means looking at an example. In the position graph on the top right, we see an object that is moving forwards but slowing down as time passes. If we want to find the velocity of that object at any instant in time, we find the slope of the line. Notice that this line starts off with a steep slope, and the slope gradually tapers off, meaning that our velocity starts off high and approaches zero. It's still a positive velocity because the object is moving forward. If we want to know the acceleration of this object, we now must consider the slope of the velocity time graph. This slope is a negative value but remaining constant. Therefore, the acceleration is a constant negative value. These are the very questions Sir Isaac Newton asked as he watched an apple fall from his apple tree. As he considered that the position's rate of change would be increasing as the apple fell, he realized that to describe its velocity, you would need to have a value that was constantly changing. There was no math at the time to describe this sort of change, and so he invented a new form of math, calculus. The first part of calculus is primarily interested with describing rates of change using something we call a derivative. If you're in calculus, you probably notice that the velocity is the rate of change of position, or the derivative of position with respect to time. And the acceleration, the rate of change of velocity, is equal to the derivative of the velocity with respect to time. Let's consider now how we might figure out how far something has traveled by looking at a velocity time graph. Consider the object shown in this graph. Here we have something that's moving forward with a speed of 3 meters per second for a time of 6 seconds. How far will it go? Pause the video if you need to take a second. In order to figure out the object's displacement or change in position, we simply multiply the speed, 3 meters per second, by the time it's been traveling, 6 seconds, and find that it will travel 18 meters. Notice that this represents the area underneath the graph, between the line for the velocity and the x-axis. Let's consider an object that's moving a little bit differently. This object starts off moving at 1.5 meters per second for 3 seconds. Then, for another 3 seconds, it moves at 3 meters per second. How far will this object travel? Pause the video if you want to do the calculation. In order to figure out the distance that this object will travel, we divide this area into 2 sections. First, we consider the portion of the motion where the object was moving more slowly, 1 meter per second times 3 seconds. Then we consider the time where the object was moving more quickly, 3 meters per second for 3 seconds. Multiplying these values and then adding them together, we find that this object will have moved 13.5 meters during this time interval. Now let's consider another object that's incrementally speeding up. The object in this graph progresses from 1 meter per second to 2 meters per second to 3 meters per second, traveling each velocity for 2 seconds. How far will this object travel? Pause the video to do your calculations. In order to find out the displacement this time, we need to break the motion into each section separately. For 2 seconds, it travels at 1 meter per second. For the second 2 seconds, it travels at 2 meters per second. And for the third section, it travels at 3 meters per second. Adding these values together, we find that this object will travel a total of 12 meters. Notice that we found the area under the graph for each of these sections. Now, what if we have an object that doesn't incrementally speed up, but speeds up constantly, like we might see in real life? How would you find the distance traveled by this object? To find the distance traveled, we could continue to break such motion into smaller and smaller intervals, assuming that it went a constant velocity that incrementally sped up. Breaking a graph like this into smaller and smaller sections and taking the area of each leads us eventually into simply taking the area underneath the smooth graph, in this case, a triangle. To find the distance that this speeding up object travels during these 6 seconds, we can simply find the area underneath that graph between the line for the velocity and the time axis. In this case, that area is a triangle. We can find its area by using 1/2 base times height, or 1/2 of 6 seconds times 3 meters per second. That gives us a total distance of 9 meters as this object speeds up. To summarize, the area underneath a velocity time graph turns out to be an object's displacement. In a similar way, the area underneath the graph of an acceleration graph turns out to be the change in an object's velocity, or delta V. Isaac Newton also considered this question as he sat under his apple tree. How far does an object travel? He asked. He did very similar calculations to what we just saw, only he gave them a fancier name. He invented the second half of calculus and called these calculations the integral. So, the distance an object travels is the integral of the velocity with respect to time. That just means we're finding the area underneath the velocity graph. Let's look at one example. Let's say you're riding your bike at 3 meters per second. You start to pedal and reach 7 meters per second after pedaling for 6 seconds. Let's look at how we can use a velocity graph to find both our acceleration and the distance that we travel during this accelerated motion. First, we'll sketch a line that represents the velocity as it changes from 3 meters per second to 7 meters per second. This takes 6 seconds. The acceleration is simply the slope of this line, the change in velocity over the change in time. Notice that this line goes up 4 meters per second and over 6 seconds to give us a slope of 0.67 meters per second squared. That was our acceleration. In order to find the distance traveled, we need to find the area between this line and the time axis. In this case, it's easiest to break this into 2 parts, the triangular part and the rectangular area. Therefore, the area becomes the area of the triangle, 1/2 of 6 times 4, plus the area of the rectangle, 6 times 3. That gives us a total displacement of 30 meters. To summarize what we've just seen, if we are looking at a position time graph, we can find the slope of the line or the slope of the lines tangent to our graph to tell us the velocity of an object. If we are looking at a velocity graph, the slope of our line tells us the object's acceleration. If we are looking at a graph of acceleration, the area between the line and the axis tells us an object's change in velocity. And if we are looking at a velocity graph, the area between the object's velocity and the time axis tells us the change in position or an object's displacement.